When illness sets in and the body burns with a fever, you need an immediate, precise medical measurement to know the exact status of the biological threat. But a standard digital thermometer has absolutely no biological awareness. It cannot actually feel hot or cold. Instead of sensing temperature directly, the device operates strictly as an interpreter, rapidly processing a chain reaction of physical and electrical forces. That familiar beep signaling a completed reading is the final step of a microscopic relay race, converting physical reality into actionable data. The process begins at the exact point of macroscopic contact. When human tissue presses firmly against the thermometer's smooth metallic tip, thermal energy begins transferring. Housed safely beneath that metal casing is a highly specialized semiconductor known as a thermistor. As biological heat enters the device, the semiconductor's internal structure absorbs energy and loosens, causing electrical resistance to drop. A constant electrical current pushes through this altering grid. Because internal resistance is dropping, the outgoing voltage shifts dynamically. This reaction happens in a fraction of a second. The physical thermal energy is immediately converted into an active, shifting electrical signal. The patient's biological heat is now successfully captured within the device, existing entirely as a measurable electrical property. Inside the microchip, a new obstacle emerges. The electrical voltage is an analog signal, a continuous, flowing wave. The thermometer's operating system only understands binary code. To cross into the computational realm, the signal is routed through an analog-to-digital converter, or ADC. This diagram shows the ADC acting as a translator. It takes the continuous analog voltage wave and systematically slices it into discrete binary values. The microcontroller grabs these digital blocks and filters them, stripping away erratic electrical noise. Next, it applies calibration corrections. The microcontroller scans a dense grid of pre-programmed mathematical conversion tables, finding the exact coordinate matching the clean digital value. A specific voltage level is assigned 35 degrees Celsius, while another maps to 37 degrees. This precise table lookup process is what finally gives cold binary data its true biological meaning. There are scenarios where direct physical contact with a patient is impossible, requiring an accurate measurement taken entirely from a distance. To achieve this, we rely on a different biological reality. Human skin continuously emits invisible infrared radiation into the surrounding air. This model outlines the alternative to the thermistor. An infrared sensor captures the invisible radiation waves, and the microchip applies physical rules, specifically the Stefan-Boltzmann law, to map the intensity of the incoming radiation directly to an estimated temperature scale. Even though the sensor collects radiant energy instead of conductive heat, the underlying system is identical. The microchip forces this data through the exact same rapid electrical-to-digital translation. Whether utilizing physical contact or infrared logic, the system relies entirely on forcing physical laws to speak digital math. The sheer computational velocity required for this is staggering. The entire sequence, absorbing energy, altering voltage, slicing the signal into digital math, and pulling coordinates from a table, loops multiple times every single second. Looking closely at the schematic of an LCD screen, we see the microcontroller's ultimate function. It pushes the final calculated value outward, illuminating the specific grid coordinates required to form a precise number. When you sit in a dimly lit room waiting for a reading to finish, the device resting under your tongue is a miniature orchestra of embedded computing and precise electronics. It captures analog biological heat, forces it through microscopic translating sensors, and delivers an exact numerical medical truth. Our ability to accurately monitor and respond to the human body relies completely on our technological capacity to capture and translate the invisible analog world.